Hello, in this video I'll be working through Unit 4 homework problems 14 through 25, and these problems deal with L'Hopital's rule. Number 14, we want to find the limit as x approaches infinity of x cubed over e to the 3x. So the first thing we're going to try is substitution. X is approaching infinity. That means it's growing without bound. It's just getting larger and larger. And so when we take something that's growing without bound and cube it, we get something that's unbounded. So infinity to the power 3 is still going to be infinitely large. Now we can't really treat infinity like a number and operate it on it like we can numbers. But we know if x is approaching infinity, then x cubed will also be approaching infinity. If you're not sure what to do with these infinities, you can also think about the graph. So the graph of x cubed looks about like that. And we're saying as x approaches infinity, so as x is getting larger and larger, what's happening to the y values? Well, they are approaching infinity. E to the 3x, we can also think about that graphically. So e to the 3x, and we have a graph that's doing something like that as x is approaching infinity. So as we move farther and farther out to the right, the graph is approaching infinity. So we get here infinity over infinity. And L'Hopital's rule tells us that if we have a limit in the form infinity over infinity, then that's going to equal the limit of the derivative of our numerator, 3x squared, over the derivative of our denominator, 3e to the 3x. And now we can evaluate this limit. We'll try this again using substitution. Well, when we substitute in an infinitely large value for x, 3 times x squared is going to be infinitely large. And 3 times e to the power 3x, when x is infinitely large, that is also going to be infinitely large. So again, we get something of the form infinity over infinity. So I'm going to apply L'Hopital's rule again, which tells us that that limit is going to equal this new limit where I take the derivative of my numerator, so I get 6x, over the derivative of my denominator, 9e to the 3x, and now we find the limit as x approaches infinity. As x approaches infinity, 6 times x is approaching infinity, and 9 times e to the power 3x is approaching infinity. So we can use L'Hopital's rule again. And this is going to equal the limit as x approaches infinity. I'll take the derivative of my numerator and get 6. Take the derivative of the denominator, I get 27e to the power 3x. And now when I substitute in an infinitely large number for x, I get 6 over infinity. And 6 over infinity is approaching 0. So my limit here is 0. Number 15, we want the limit as x approaches infinity, natural log of x over x squared. So I try substitution. The natural log of an infinitely large number is infinitely large. And then an infinitely large number squared is still infinitely large. So I have infinity over infinity. So I can apply L'Hopital's rule. So I'm going to take the limit as x approaches infinity of the derivative of my numerator. The derivative of natural log of x is 1 over x, over the derivative of my denominator, which is 2x. And then I can try substitution again. If I try substitution here, 1 over an infinitely large number is approaching 0. So I would have 0 over infinity. 0 over infinity might seem a little confusing. Well, what if we simplified this algebraically? So limit as x approaches infinity, 1 over x divided by 2x is 1 over 2x squared, right? Instead of dividing by 2x, we can multiply by 1 over 2x. And now, when I let x approach an infinitely large number, I have 1 over an infinitely large number, so I know that that is approaching 0. So my limit is equal to 0. Number 16, we're going to find the limit as x approaches infinity of x squared minus 9x plus 4 over 3x squared plus 7x plus 8. Now, if we let x approach an infinitely large number, then we're just going to get infinity over infinity. So we can use L'Hopital's rule. Now, you might recognize this type of limit problem. We've encountered this before, and we had some shortcut rules. If x is approaching infinity, and our numerator and denominator are both polynomials, then we can compare the degree. So the degree in my numerator is 2. The degree in my denominator is also 2. Since they have the same degree, my limit is just going to be the ratio of these leading coefficients here, or 1/3. So I know the answer is 1/3, but I'm going to show you how we can find this using L'Hopital's rule. Since we get infinity over infinity, I can set this equal to the limit of the derivative of the numerator over the derivative of the denominator. So the derivative of my numerator, 2x minus 9, and my denominator, 6x plus 7. And now substitution is giving me infinity over infinity again, but I can apply L'Hopital's rule again. Derivative of 2x minus 9 is 2. Derivative of 6x plus 7 is 6. And 2 over 6 is 1/3. So our limit is equal to 1/3. 17, limit as x approaches infinity of x squared plus 4 over 8 to the power x. X is approaching an infinitely large number. So in the numerator, we have an infinitely large value. In the denominator, 8 to the power of an infinitely large number is also going to be an infinitely large number. So this is in the form of infinity over infinity. Now, I don't really need L'Hopital's rule here. I can reason this out. I have a polynomial in my numerator. I have an exponential function in my denominator. And I know exponential functions grow faster than polynomials. So overall, this limit is going to equal 0. But just for the sake of showing mathematically why this happens, we can apply L'Hopital's rule and take the limit as x approaches infinity of, now the derivative of my numerator is 2x, derivative of my denominator, 8 to the power x times the natural log of 8. As x approaches infinity, this is still giving me infinity over infinity, so I can apply L'Hopital's rule again. The derivative of my numerator is 2. The derivative of my denominator is 8 to the power x times the natural log of 8 times the natural log of 8. And so now this is giving me 2 over an infinitely large value, which is approaching 0. 18. Limit as x approaches infinity, x squared plus 3x over x times the natural log of x. Substitution is going to give me infinity over infinity. So I can apply L'Hopital's rule. I could also, like we did in the last problem, reason this out by looking at how quickly these functions grow. So x squared plus 3x, that's a polynomial degree 2. In the denominator, we have x times ln x. So x is polynomial degree 1. Natural log of x grows more slowly than polynomial degree 1. So we have a situation where the numerator is growing faster than our denominator. And so this limit should end up being infinite. But let's see what happens when we apply L'Hopital's rule. So this is going to equal the limit as x approaches infinity. I'm going to take the derivative of the top. I get 2x plus 3. Now the derivative of the bottom, I need to use product rule here. So it's the derivative of x times ln x plus x times the derivative of ln x. The derivative of ln x is 1 over x. So I have x times 1 over x, and that simplifies to just 1. Substitution here is going to give me infinity over infinity. The natural log of x as x approaches infinity is infinity. And if you're not quite sure why that is, think about the graph of ln x. So as x is approaching infinity, our y values here are also approaching infinity. Very slowly. This is increasing very slowly, but it is always increasing. So we can apply L'Hopital's rule again and get the limit as x approaches infinity. Derivative of 2x plus 3 is 2. In my denominator, derivative of ln x is 1 over x. And then the derivative of plus 1 is just 0. Algebraically, this simplifies to the limit as x approaches infinity of 2x. Right? 2 divided by 1 over x is the same as 2 times x over 1. And now as x approaches infinity, this limit is approaching infinity. 19. Limit as x approaches infinity, x times the sine of 5 over x. Well, substitution here gives infinity times the sine of 0, and the sine of 0 is 0. Infinity times 0 is an indeterminate form. We don't know what that's equal to. It could equal a variety of different things. So we need to work with this algebraically. It's not in a form right now where I can use L'Hopital's rule, but I can rewrite this. I can think of x as 1 over 1 over x. Okay, those are equivalent. If I take my x and I move it down to my denominator, so instead of having x, if I move it down to my denominator, instead of having x over 1, if I move the x down to the denominator, the exponent becomes negative, like so. So here it's in the numerator, it's x to the positive 1. If I move it down to the denominator, it becomes x to the power negative 1. And x to the power negative 1 is the same as 1 over x. So I have 1 over x. That's just equal to x. So I'm going to rewrite this problem. Limit as x approaches infinity. Instead of x, I'm going to write 1 over x times, and then I have the sine of 5 over x. So now this is the limit as x approaches infinity. The sine of 5 over x over 1 over x. And the reason I've written it like this is because now substitution gives, when x is an infinitely large number, 5 over an infinitely large number is approaching 0. The sine of 0 is 0. And in my denominator, 1 over an infinitely large value is approaching 0. So now I have 0 over 0. And in this form, I can use L'Hopital's rule. So we're going to apply L'Hopital's rule to this limit right here. So that limit is going to equal the limit of as x approaches infinity of the derivative of sine of 5 over x. I need to use the chain rule here. This is in the form of sine of stuff. So the derivative of sine of stuff is cosine of stuff times the derivative of the stuff. On the bottom, the derivative of 1 over x, negative 1 over x squared. Now we can simplify this algebraically. The negative 5 over x squared divided by negative 1 over x squared is just 5. If you're not sure how I got that, you can also, instead of dividing by negative 1 over x squared, flip and multiply. So multiply by negative x squared. And that's going to give us limit as x approaches infinity, cosine of 5 over x times 5. And we move the 5 to the front. And now substituting in an infinitely large value for x, 5 over an infinitely large value is approaching 0. The cosine of 0 is 1. 1 times 5 is 5. So my final answer, the limit, is 5. Number 20, we want the limit as x approaches infinity, x times the tangent of 7 over x. Substitution here is going to give infinity times the tangent of 0. The tangent of 0 is 0. So we have this weird kind of indeterminate form here. It's not infinity over infinity or 0 over 0, so I can't use L'Hopital's rule. But I can rewrite this algebraically like we did in the last problem. I'm going to leave the tan of 7 over x as is, but I'm going to rewrite x as 1 over x. And now substitution gives the tangent of 0, which is 0, over 1 over an infinitely large number is approaching 0. So now I have something in the form of 0 over 0. So I can apply L'Hopital's rule to this limit here and get limit as x approaches infinity. The derivative of tan of 7 over x, we need to use chain rule. This is in the form of tan of stuff. The derivative of tan stuff is secant squared stuff times the derivative of the stuff. And then in the denominator, derivative of 1 over x is negative 1 over x squared. Negative 7 over x squared divided by negative 1 over x squared is 7. So now I have limit as x approaches infinity of 7 times secant squared 7 over x. As x approaches infinity, 7 over x is approaching 0. So this is 7 times secant squared of 0. And secant squared is the reciprocal of cosine squared. So it's 7 over cosine squared of 0. The cosine of 0 is 1. So my limit is just 7. Number 21, limit as x approaches infinity. Arctan 3x minus pi over 2 over arctan 7x minus pi over 2. So first we'll try substitution. The limit as x approaches infinity of arctan 3 times x. Let's think about the graph of arctan. Arctan is the inverse of tangent. So our arctan function has a horizontal asymptote at pi over 2 and another horizontal asymptote down here at negative pi over 2. Passes through the point 0, 0. And it's an increasing function. Concave up on the left, concave down on the right. So here's what our graph of arctan looks like. And with this limit, I want to know what is the arctangent of an infinitely large x value. So if x is infinitely large and positive, then arctan is approaching pi over 2. So this is going to be pi over 2 minus pi over 2 over, and then arctan of 7 times x, well, that's still taking the arctan of an infinitely large number. So pi over 2 minus pi over 2. So this is in the form of 0 over 0. We can apply L'Hopital's rule. So this limit is going to equal the limit as x approaches infinity. Now we need the derivative of arctan 3x. We need to use chain rule. The derivative of arctan stuff is 1 over 1 plus stuff squared times the derivative of the stuff. The derivative of 3x is 3. And then I have minus the derivative of pi over 2, well, that's just 0. In the denominator, derivative of arctan of 7x. So arctan of stuff is 1 over 1 plus stuff squared times the derivative of the stuff, and then minus 0. So the minus zeros I don't need. And let's rewrite this so it's easier to see what's happening here. We've got 3 over 1 plus 9x squared divided by, I'm going to flip and multiply, 1 plus 49x squared over 7. And I want the limit as x approaches infinity. These are now polynomials in our numerator and denominator, so we can kind of apply our shortcut. I've got 3 plus 49 times 3 is 147x squared over 7 plus 63x squared. Now we can go through L'Hopital's rule here. We'll have to use it repeatedly to get rid of our x terms. Or we can just use the fact that our numerator and denominator have the same degree And since x is approaching infinity, we can just use the ratio of our coefficients, which reduces to 7/3. 22. Let f and g be differentiable functions about which the following information is known. F of 3 equals g of 3 equals 0. We also have f prime of 3 equals g prime of 3 equals 0. We know f double prime of 3 equals -2. And g double prime of 3 is +1. Let a new function h be given by the rule h of x equals f of x over g of x. On the same set of axes, we want to sketch possible graphs of f and g near x equals 3. And then use the provided information to determine the value of the limit of h of x as x approaches 3. So let's go back to our clues. F of 3 and g of 3 are both 0, so they both pass through this point here on the graph. F prime of 3 and g prime of 3 are both 0, so we can expect to have a relative max or a relative min at that point. We don't know that for sure, but it's possible. And then f double prime of 3 equals -2. That tells me that f is concave down at 3. So f, if it's concave down and the first derivative is 0, is going to have a relative max. So there's my f. G double prime of 3 is +1. And since the second derivative of g is positive, I know that g is concave up. So g could look like this. Concave up, the first derivative is 0. And it's passing through that point. I missed my mark a little bit there. We want the limit of h of x as x approaches 3. Well, that's going to be the limit as x approaches 3 of f of x over g of x. And using substitution, that limit would be f of 3 over g of 3. But f of 3 and g of 3 are both equal to 0, so that gives us 0/0, which is an indeterminate form. It does, however, allow us to use L'Hopital's rule. So this is going to equal the limit as x approaches 3 of f prime of x over g prime of x. Using substitution, that gives us f prime of 3 over g prime of 3, but f prime of 3 and g prime of 3 are both equal to 0. So again, we get 0/0, which is indeterminate. But we can use L'Hopital's rule again. Limit as x approaches 3. Now I want the derivative of f prime of x, which is f double prime of x, divided by the derivative of g prime of x, or g double prime x. Evaluating that at 3 gives f double prime of 3 over g double prime of 3. F double prime of 3 is -2, g double prime of 3 is 1, so our limit is -2. Number 23. Find all vertical and horizontal asymptotes for the function r of x equals 3 times x minus a times x minus b over 5 times x minus a times x minus c, where a, b, and c are distinct arbitrary constants. In addition, we're going to state all values of x for which r is not continuous, and then sketch a possible graph of r, clearly labeling the values of a, b, and c. Well, since x minus a is a common factor of my numerator and my denominator, I know there's a removable discontinuity when x is a. And a removable discontinuity is going to look like a hole in the graph. At x equals a. To find my vertical asymptote, I'm going to set the denominator equal to 0 and solve. So 5 times x minus c equals 0. That has a solution at x equals c. And as long as c doesn't also make the numerator 0, and since it tells us that b and c are distinct, we know that won't be the case, then here I have a vertical asymptote. So vertical asymptote at x equals c. To find my horizontal asymptote, I want to find the limit as x approaches infinity of r of x. And I can use the simplified version after I cancel out the x minus a's. So it's 3 times x minus b over 5 times x minus c. Substitution is going to give infinity over infinity. So we can use our shortcut rule. Since these are polynomials, they're both the same degree. I can just look at the ratio of my leading coefficients. I know this limit is going to be 3/5. We can also apply L'Hopital's rule here, since we are getting a limit in the form of infinity over infinity, in which case we'd have limit as x approaches infinity of the derivative of 3 times x minus b is 3. The limit of 5 times x minus c is 5. And so we're getting a limit of 3/5. Now I should also check for horizontal asymptotes on the left end of the graph. So as x approaches negative infinity, the exact same thing is going to happen, and we're going to get 3/5. So we have a horizontal asymptote at y equals 3/5. We were asked to state all discontinuities, so the vertical asymptote here is a discontinuity. That one is called an infinite discontinuity. So we have an infinite discontinuity at x equals c, and then we were asked to sketch a possible graph showing where these values are. So here's y equals 1. I know I have a horizontal asymptote at 3/5. I have a vertical asymptote at x equals c, and really it's my choice where I want to put that. And I'm just going to sketch a graph that follows my asymptotes here and here, and then here and here. So I still need to put C on my graph somewhere. Nope, C we have. That's our vertical asymptote. I need to put my removable discontinuity at A. And it's my choice where I want that to be. So I can put it right here. I'm going to draw an open circle and then erase the inside there. And that is where I chose to put my value for A. And then B doesn't have any kind of distinct feature of the graph, so we could put B wherever we want. I'm just going to put B over here. Okay, so we have vertical asymptote at x equals c. We have our horizontal asymptote at y equals 3/5. And we have removable discontinuity at x equals a. Number 24. Consider the function g of x equals x to the power 2x, which is defined for all x greater than 0. Observe that the limit as x approaches 0 from the right of g of x is indeterminate due to its form of 0 to the power 0. So if we substitute in 0, we get 0 raised to the power 0. That is an indeterminate form. 0 to the power 0 is an indeterminate form. Part A, we're asked to let h of x equal the natural log of g of x. Explain why h of x equals 2x times ln x. Well, if we compose our function here, that equals the natural log of, and then since g of x is x to the power 2x, I can use my log properties and rewrite this where I move the power down in front of the log as 2x times the natural log of x. Next, we're asked to explain why it is equivalent to write h of x equals 2 ln x over 1 over x. And we've seen this kind of trick before. This x right here, that is x to the power positive 1. If I move it down into the denominator, it becomes x to the power negative 1. And x to the power negative 1 is 1 over x. So then I can rewrite it as a 1 over x. Part C, use L'Hopital's rule and your work in Part B to compute the limit of h as x approaches 0 from the right. So now substitution, so the limit x approaches 0 from the right of 2 ln x over 1 over x. Now substitution gives 2 times the natural log of 0. Think about the graph for ln x. So the natural log of 0 is undefined, but we're approaching 0 from the right-hand side. So as we're approaching 0 from the right-hand side, ln x is approaching negative infinity. So that's giving negative infinity here. In the denominator, 1 over 0 from the right-hand side. So we look at the graph of 1 over x. The graph of 1 over x looks like this. As I'm approaching 0 from the right-hand side, the graph is approaching positive infinity. So this is in one of our indeterminate forms that allows us to use L'Hopital's rule. So this is going to equal the limit as x approaches 0 from the right-hand side, 2 times the derivative of ln x, so 2 times 1 over x, over the derivative of 1 over x is negative 1 over x squared. Now if I simplify this, so instead of dividing by negative 1 over x squared, I flip and multiply. I have 2 times 1 over x times negative x squared is just going to give me negative 2x. And then when I find that limit using substitution, I get 0. Part D, based on the value of that limit, find the limit as x approaches 0 from the right of g of x. Well, we know that the limit of h of x, okay, the limit of h of x as x approaches 0 from the right is equal to 0. This is the limit as x approaches 0 from the right. H of x is equal to ln of g of x. So that's equal to 0. And then we have our limit property that allows us to interchange the limit and the function. So the limit of the log is equal to the log of the limit. So I can write the natural log of the limit as x approaches 0 from the right of g of x equals 0. So I've switched the limit and the log here. And we know that the natural log of 1 equals 0, so that means what's in the brackets here must equal 1. This says the natural log of stuff equals 0. Well, the natural log of 1 equals 0, so the stuff must equal 1. And we're trying to find the stuff. So our limit as x approaches 0 from the right of g of x, we know must equal 1. And number 25, recall we say that a function g dominates function f provided that the limit of f as x approaches infinity is infinity, the limit of g as x approaches infinity is infinity, and the limit of f of x over g of x as x approaches infinity equals 0. So let me write that out. The limit of f of x over g of x as x approaches infinity equals 0. If this is the case, then we say that g of x dominates f of x. It's growing at a faster rate, so the limit is going to equal 0. The one that's growing at a faster rate is the one that's dominating the other one. So part A, which function dominates the other? ln x or square root of x? Well, the natural log function grows more slowly than the square root function. So the square root function is the one that dominates. Part B, which function dominates the other? Natural log of x or the nth root of x for positive integer values of n. Well, again, the natural log function is going to grow more slowly. So the nth root of x in general is going to dominate our natural log function. Part C, explain why e to the x will dominate any polynomial. Well, e to the x, in the long run, for large enough values of x, is going to grow at a faster rate than any polynomial will. So e to the x would dominate a polynomial for large values of x. And then part D, why does x to the n dominate ln x? Well, same reason, x to the power n for large values of x is going to grow faster than the natural log of x. So x to the power n will dominate ln x. ln x is pretty much the slowest growing function of all the functions that we study. So this can help us when we're finding limits. We don't really need to apply L'Hopital's rule if we can tell, if we're taking the limit of a fraction and we can tell which one dominates the other. Whenever it's the denominator that's dominant, our limit is going to be 0. If it's the numerator that's dominant, our limit is going to be infinite. Okay, that wraps up our problems on L'Hopital's rule.